Hello, everyone, and thank you as ever for listening to our programme each week. The purpose of this announcement is to let you know how we got on with the donation drive that we ran over Christmas. This was to raise funds for two purposes. One, to help us to meet the costs of producing this show each year, and two, to rebuild our website, which, unlike our radio programmes and our podcasts, was not going to win us any awards anytime soon. Well, thanks to your generosity, we raised close to £10,000. And we've invested that money in a brand new website that's now complete and it's wonderfully easy to use. Do please take a look. It's at thenakedscientist.com. All of the programmes we've made over the years are there and free to download, as well as hundreds of science articles and features penned by researchers from all over the world. Also, the discussion forum has had a major makeover too. We hope you like it. I do have a list of the names of all of you who so kindly helped us, and where possible, I will be writing to you personally as soon as I can to thank you. And if you didn't manage to make a donation before, but you would still like to, then the system is still operating, and you can find it at nakedscientist.com/donate. Thank you again from me and the team.
I have you loud and clear.
Hello. Welcome. Science.
And that is to say,
Physics,
medicine,
nature,
or
Space. Time.
the brain,
Life. The universe.
2017 marks 100 years since we first split the atom. So this week we're going inside the average atom to find out what they're made of and how physicists are creating entirely new supermassive atoms that have never existed on Earth before.
Plus, in the news, a drug that reverses the aging process, a new way to make millions of brain, muscle, or blood cells in a matter of days, and a big shake-up in the world of dinosaur fossils. I'm Georgia Mills.
And I'm Chris Smith, and you're listening to The Naked Scientists.
The Naked Scientists podcast is powered by ukfast.co.uk.
First this week, a drug that reverses the ageing process has been unveiled by scientists in the Netherlands. Administered to mice that were the rodent equivalent of human 80-year-olds, the agent triggered the animals to recover lost hair, move with renewed vigour, and also reversed age-related decline in their kidney function. The drug causes worn-out or senescent cells to kill themselves, preventing them from exerting harmful effects on surrounding healthy tissue. And it works by prizing a cell signal, which is called P53, away from the clutches of another protein, which is called FOXO4, and this triggers the senescent cell to die. Peter de Keyser created it.
Senescence is a state of hibernation. It can occur in cells that are irreparably damaged, that cannot cope with the damage, and they basically stop dividing. That's in principle a good thing, because you don't want damaged cells going rogue. However, these cells secrete a whole range of factors that are unwanted. As we age, we get more and more of these senescent cells, therefore we also get more and more of these unwanted factors in our environment of the body. And it's actually shown that taking out these senescent cells from mice makes them live longer.
Why would the body elect to hang on to these cells, which are, for want of a better word, just sort of sitting there poisoning the well? Why doesn't it get rid of them?
It is thought that early in life these so-called senescent cells have a benefit over cell death. So if a cell is irreparably damaged and chooses to die, if we have this too often in our bodies, then we would remain very tiny. And we would be outcompeted by nature back, when we were still running around in bearskins. So early in life, it is beneficial to have these senescent cells over dying cells. However, we were never meant to become 80 years of age. And as we age, we get more and more of these senescent cells, and that's when they start becoming problematic.
And what sorts of factors do they squirt out into the body, these senescent cells, which have a deleterious effect?
Over 100 different kinds of proteins have been identified to be secreted. Some prominent ones are interleukins, which are pro-inflammatory factors. Also proteases, which break down the matrix of our tissues, for instance, so that's undesirable. And also there are plenty of growth factors, which can actually promote tumor growth, for instance.
And you think you may have a way to skew whether or not they choose to become senescent or to die off?
From a fundamental research point of view, we try to figure out, why is it some cell types die and others do not? They go into senescence. I tried to figure out what could be the molecular switch. And we identified a protein, and that's the pivot between death and rest. And by making something to resemble this protein, I could fool the system, and therefore we could eliminate these senescent cells.
And does that mean then that if you were to administer that signal into, say, an old animal, that you could rid the animal's tissues of these senescent cells which are contributing to the aging process, and therefore you could, at the very worst, potentially arrest aging and maybe even wind the clock back a bit?
Yeah, you're spot on, actually. That's exactly the case. So we started off in petri dishes with cells. And there, if we make those cells senescent, we could eliminate them by adding this compound. And if we did this then in mice that were about 2.5 years of age, which is roughly 80 years in terms of human years, they have, for instance, worse fitness. The hair loss is a feature. They have worsened organ function. And we could normalize those levels with using this compound.
Right, so you actually can reverse some of those signs of aging in these mice.
I think that's the big novelty of this study. So far, much of the anti-aging research has focused on delaying aging, for instance, eating less and exercising more. But society actually shows the reverse. We exercise less and we eat more. So this is a message that doesn't really appeal to the general audience. What we now show is that it's actually possible that when you're already aged, that we can actually reverse some of these effects. And that's the big novelty of this study.
What is this stuff, and where can I get some, more importantly?
So this chemical is actually part of a protein called FOXO4, and it's physically associated to another protein, which is called P53. What I designed is a small piece of protein that it releases P53, and that leads to cell death.
So essentially what we've got is this FOXO4 sitting there, and in a senescent cell which is just stewing and being miserable, it's grabbed the P53 molecule, and in that situation the cell just sits and stews. Your drug molecule gets between those two, stops the FOXO4 from grabbing the P53, and the P53 then triggers the cell instead to die.
That's absolutely correct.
Now, the critical question, of course, though, is whether this stuff does harm, because it sounds too good to be true. What happened to the mice that you administered this to? And what happens to a healthy mouse you give it to? Do they have side effects?
So that's also a very important question that we were having. I mean, that's also why this study took us so long. And we showed that there was no toxicity. We've been treating mice, healthy mice, for over a year now. We start at 1 year of age, which is around 30-40 years in mouse years, and we treat them for over a year, so another 30-40 years, and they still do not show any negative symptoms. So there's no accelerated cancer development, there's no effects on the blood system. So as far as we can tell, this is perfectly safe to healthy mice.
But will it work in humans? Well, we're all going to have to age a little bit more while we wait for Peter to find out. That was Peter de Keyser from Erasmus Medical Centre in Rotterdam, and that study just came out in the journal Cell.
To technology now, and with us is entrepreneur and angel investor Peter Cowley, who scans the industrial horizon for us. On his radar this week, user interfaces in cars. What's that all about, Peter?
Yes, I noticed a couple of weeks ago that a company called Gesticon, a German company, which I met in Vienna some time ago, had been sold to a French automotive company. So I started to think about user interfaces on cars, which started very simply a long time ago with a Model T Ford, which had had one on-off switch and 1 meter. And of course, has got massively complicated since then. Slightly less complicated because we've got screens and touch screens. But if you go back to a car 20 years ago, it might have had 100, 120 buttons on it.
All right, so this is the idea of people interacting with their cars.
Yes, with not just obviously the indicators and lights, but all the other things, the entertainment system, the sat-nav, the telephone, etc. And so there are two elements to this. There's the output, which is effectively what you need to see, which is the screen. Maybe it's some sort of voice-generated information, or maybe the head-up display, which is the one that you get in some cars, which sits in front of you, projected onto the windscreen, and then the inputs. And the outputs aren't really too much of a problem. You can get distracted by them, but you're more likely to get distracted by actually interacting with the device. If you're doing it with voice, which many cars have, but in my view never seem to work that well, you've got something there. Otherwise, it's knobs and buttons. Once on the wheel are okay, or some sort of touch screen. And what's happening in recent times is that people are wanting more and more information which is similar to that on their mobile phones. So there are a number of systems from Apple, from Google, etc., which actually convert what's happening on a phone onto the screen, which means they don't have to build in the complex technology inside the car. And you can have your address book, you can have your music, etc., actually projected onto the into the car.
Oh, well, floating up there, because I suppose when you're driving, you do not want to be fiddling around with complex, fiddly things. You want it to be as simple as possible. So how are these companies trying to make it easy for you to interact with your car?
Yes, the one extreme, you've got the Tesla, which has got a 17-inch display in there, which is a great big thing that replaces a central console, which would be very tempting to browse the internet on, which would be fine if you had an autonomous vehicle, but clearly not if you're having to drive. At the other end, this Gesticon company is actually monitoring the hands on the wheel and monitoring the fingers, and it can detect where the fingers are in space, effectively, so you can then either learn or teach it to recognise what volume up and volume down are, and changing the sat-nav by selecting letters, etc.
Okay, and if I do jazz hands, turn the music up, that kind of thing.
Well, it could be as complicated as that, but that actually means you have to take your hands off the steering wheel, I
don't
suspect.
do that.
So don't do that, exactly. But the bigger issue, of course, is the fact that there's too many people with phones in the cars, and the real serious danger of using your phone while you're driving. And the figures are showing that in the UK that the number of road deaths is actually creeping back up again, even though it's been going down for many years. And the suspicion is that people are using texting and using the phone rather than the car.
So all this new technology, there's a danger that it will, instead of helping us, will distract us more from what's actually going on the roads.
Absolutely, it is doing that already. I mean, in the medium term, autonomous vehicles means you can go to sleep in the car. You shouldn't worry about this at all. But in the meantime, somehow, there's got to be something in there that actually stops us picking up, or not us, it's mainly younger people, unfortunately, that's picking up the phone and doing things that they really, really mustn't do.
It's too tempting to go on social media while they're
When
doing the long
along.
journeys.
Yeah, exactly.
When will we see this across all cars, do you think, this sort of brilliant interface where you can say, car, take me here, or car, turn up the volume, or wave your hands?
With the voice, that's sort of supposed to be there already, but I've never had really worked for me. But if you take it in terms of the mobile devices, many of them, there are not just the big electronic manufacturers like Apple, but there are many cars like BMW and Ford have already got those built in.
Wow, I look forward to it. Thank you so much, Peter. That was
Thank
Peter
you very
Cowley.
much. Thank you.
Why do bees make hexagonal honeycombs? And what gives each snowflake its unique shape? The answer is that nature does that through the laws of physics. And in his new book, Forces of Nature, Brian Cox explains how. Based on the acclaimed BBC TV series of the same name, this new paperback release is a beautiful exploration of our planet, and it provides the deepest answers to some of the simplest questions. Forces of Nature is on sale now. You're listening to The Naked Scientists with me, Chris Smith, and also with Georgia Mills.
Still to come, a dinosaur family tree shakedown and a look at the mysterious eyes of the mantis shrimp.
But first, stem cells are the starting point for all of the cells in the human body, and scientists can use them to replace injured tissues, or if they want to study how a certain disease affects a different part of the body, they can model it in a dish using stem cells. But it can take a really long time, in fact up to 20 weeks, to turn a stem cell into a mature tissue. Well, now scientists at the University of Cambridge and the Wellcome Trust Sanger Institute have reduced that to just a matter of days, thanks to a new technique that can make millions of identical cells at once. To find out how, Cambridge University's Daniel Ortman is with us. Hello, Daniel.
Hi.
So first of all, tell us, how did you do this?
So essentially we focus on a process called reprogramming cells. So essentially it's turning one cell type directly into another. So rather than going down this fairly lengthy developmental process, we just convert them directly from, let's say, a skin cell, or in our case, a stem cell.
So in the old days, we used to sort of take a skin cell and turn it back into a stem cell, and then turn the stem cell back into what we wanted to turn it into. Yeah. You're saying, well, we're going to short circuit that equation and go from A to B directly rather than via C.
Yeah, exactly. So reprogramming processes are fairly direct because you don't have to go through this cascades of normal development as it happens in the body.
Why didn't scientists do that in the first place then? Why did they go all the way back to stem cells and then turn the stem cells into what they wanted? Why didn't they do what you've now done?
I mean, people have done similar things before. It's just that what we've done in our study is rather than putting those genes that control the whole process, putting those randomly into the cell, what we did, we integrated this genetic information in specific locations into the genome. They're called safe harbors. And so in this way, we can actually ensure that all the cells have the same information And we can also rapidly turn it on and then switch this program that's running into the cells.
Right, so you embed the reprogramming genetic information into the cell at the get-go.
Yeah, exactly.
And then you can control what's turned on, where and when. So that cell passes all of that genetic information into its offspring. So you get a whole clutch of cells that are the same. They'll behave the same way, follow the same instructions.
Yeah, so essentially we are putting in the information and then it just sits there until we decide to give it a chemical trigger to then activate those genes. And then the cells rapidly actually reprogram, and then within, as you said, 5 or 6 days, they turn into an entirely different cell type.
And so when you say there's a safe harbour, so you put the instructions, you know what the genetic instructions are that turn a skin cell into, let's say, a heart cell or something. So you'd put those genes into a specific part of the genome where you know they're not going to do any damage to the cell putting them in there.
Yeah, exactly. So there are some defined sites where people studied what are those locations doing, and also at the same time those locations are also protected from events like silencing. So usually when you put something somewhere in the genome, it's very likely that the cell kind of shuts it down. So it doesn't want this kind of strange information to be there and to be read. So it has actually mechanisms of shutting it off. Whereas when you put it in the genomic safe harbors, it's much less likely that happens.
How do we know these cells are safe that you make with this, if you wanted to use them therapeutically? Because at the end of the day, having enough stem cells or mature tissue cells that can do something has always been a problem.
Yeah.
How do you know they're safe?
So you're talking about cell therapies now. So there's various ways to test whether the cells are actually safe. I mean, obviously, we can make them in the lab first and then have them there and do all sorts of tests on proliferation and genomic stability to really ensure that the cells would be safe then to put into a patient. But for the more immediate applications, what we can do is we produce all sorts of cell types that are hard to come by from humans. So like brain cells, heart cells, all those type of cells, to actually make them in a controlled way and in large quantities so that we can use them for drug discovery or screening processes within the pharmaceutical industry, for example.
Now, when you say you turn a cell into, say, a muscle cell, how do you know it really is a muscle cell? Because it might look like one, but biochemically, have you checked to see that, okay, that's a muscle cell? And also epigenetically, have you looked at the genes which are being turned on and off? Is that, to all intents and purposes, now a muscle cell that you've made?
Yeah, exactly. So what we do is, after we turn on those genes, we actually check other genes that are unrelated to the ones we activated, and whether they come up or not. So that gives us an idea of is this program of being a muscle cell actually activated in those cells.
It's got the sort of genetic fingerprint of a muscle, so you can be confident that's what you've got.
Yeah, and then you can also obviously do epigenetic tests, but what we also did was functional tests. So we actually gave them the same kind of compounds that make muscle cells contract, for example, in the body. And if we add those to the dish, then the cells are contracting. So essentially, functionally, also they are exactly what we would expect them to be.
Daniel Ortman there, and his study came out in Stem Cell Reports.
Now, if your family tree is muddled up, you could end up drawing some pretty incorrect conclusions about where you came from. Well, now the entire dinosaur family tree has been called into question, which could mean we've been making mistakes when looking at how they evolved and where they came from. Scientists have always classified dinosaurs very neatly into two simple groups, those with bird-like hips and those with lizard-like hips. It's been the conventional wisdom for almost 130 years, but this week a paper published in Nature suggests we may need a shakedown and reclassification of the entire dino family tree. I went to look at some fossils with the lead author and PhD student at Cambridge University, Matthew Barron.
We're currently standing in the main gallery of the Cedric Museum in Cambridge, which is the university's Earth Science and Paleontology Museum.
We've got quite a few dinosaurs around us, which is very exciting. So could you tell me a bit about how dinosaurs are classified at the moment?
So the traditional model that's been around since the late 1800s was proposed by a Cambridge scientist called Seeley. And his idea was all dinosaurs were either this one category or they're in this other category. So on the one hand, we had what were called ornithischians. This is the bird-hipped dinosaurs, not the birds, but the bird-hipped dinosaurs. And examples include Triceratops and Stegosaurus and this iguanodon that we're stood in front of.
Let's go look at Iguanodon, because this thing is towering above us. It's standing on two legs, it's got a massive tail, it's got a rib cage I could comfortably get in, and then this giant head.
These guys were sort of the cows, very large cows of the Jurassic and Cretaceous, large family of herbivores. So they are the ornithischians. And then on the other hand, all the other dinosaurs were lumped into another group called Saurischia, which means lizard-hipped. So their hips look more like primitive reptiles than birds. Saurischia is made up of, in the old model, theropods, which are the meat eaters.
Like T-Rex.
Just like T-Rex, and many earlier forms, and eventually birds. And the other group are the sauropodomorphs, which some people shorten to sauropods. And they are the long-necked tree browsers like Diplodocus, Dippy at the Natural History Museum, Brontosaurus, Brachiosaurus.
So those groups, in some ways, they make quite a lot of sense. There's the bird-hipped dinosaurs and the lizard-hipped dinosaurs. But then again, you have one group, which is all the sort of the veggies, like Triceratops, Stegosaurus. But then you have this other group, which contains all the sort of two-legged carnivores, but then these massive four-legged Diplodocus-like creatures. So you've looked at these groups and you've thought, no. So can you tell me what you've done and what you've found?
We started looking at as many early dinosaurs as we could. And we built a long list of specimens we thought were relevant and interesting in early dinosaur evolution. We cross-examined them for a very large list of anatomical features, and we built a data set, the largest ever data set of early dinosaurs. And our computer software worked out for us various ways in which they could be related, which would be the most likely given certain circumstances. And what we found was the old groupings that have always been thought to exist were just not recovered in our analysis. They were not supported by the anatomy, by the data. Our data suggests that the meat-eating theropods are more closely related to ornithischians like Triceratops than either of those groups are to the long-necked tree browsers.
So you, looking at dinosaurs, you don't have the luxury of just popping them all in a DNA analysis. So you have to look at all of their physical traits and then pump all that into a computer which can look at the similarities and the differences and work out the most likely scenario for the family tree.
Yeah, essentially we are limited by the skeleton. All we have to work on is the skeleton and features of the skeleton. So we had to look at a lot of skeletons to see what features might be useful and what might not be. We tried to be as objective as possible. And then, we built this very large data set where each specimen was given a score for each feature that we thought was relevant. It was about 35,000 individual data points that we had to enter by hand. I had to enter by hand. And eventually we were able to put together this huge data set after 3 years, and it produced drastically different results.
Yeah, so this is challenging about, you said over 100 years of the accepted theory. I remember learning about this in my textbooks and in museums and things like that. So this is quite a bold reshuffle you're proposing.
It is, yeah, and we're expecting, some degree of backlash. But that's just how science works. We have a hypothesis, we get new data, we look at old data in new ways, and we present new hypotheses, and we test them again. But yes, the old scheme was the fundamental fact on dinosaurs in kids' books, in museums, and maybe they're all going to need a rewrite.
Do you suspect there's going to be quite a big debate following this paper?
I certainly hope so, yeah. I'm looking forward to the next big conference where I have to face all of the people that may disagree with me. But such is science, we put that idea out there now, and this flies in the face of 130 years of thinking. Completely disagrees with some very prominent people's PhD theses and is sort of drastically different to anything we've ever thought. So yes, there's going to be some flack.
Certainly going to be some bones of contention then. That was Matt Barron from Cambridge University.
Ba-bum. Now, in recent days, Cambridge has been in the throes of its Science Festival, and it's one of the UK's largest and most successful science festivals, actually. And to celebrate the end of the festival, we've invited the winner of this year's Cambridge Regional Fame Lab. Now, this is the competition, if you haven't heard of it, where researchers have to give a 3-minute science talk to come and join us. That's Kate Feller. Kate, tell us, first of all, who are you and what do you do?
Well, I am a postdoctoral researcher in the Physiology, Development and Neuroscience department here at Cambridge, and I study the eyes of mantis shrimp. Historically, my PhD training was studying the eyes of these remarkable crustaceans and their babies. What's so amazing about them is that the adults at least can see beyond the spectrum that we can see, that they can see all the colors of the rainbow, plus they can see different colors of ultraviolet light, and they can see the different types of polarized light. So they just have these remarkable eyes, and they've got one of the fastest animal movements on the planet, where they can strike their prey or something that's bugging them with these awesome raptorial appendages, and they can do it as fast as a bullet out of a gun.
I thought that was my daughter asking me for pocket money. That's pretty fast as well.
Yeah.
Now, why did you decide to go for FameLab? And what's FameLab for people who are not initiated?
So FameLab is... it's a science communication contest to try and encourage researchers to, I guess, be more effective science communicators. And I kind of did it on a whim. I was in the middle of my field work working in Spain, and I got an email, and I said, hey, this sounds like fun.
Well, you must be good at it. We're going to find out, I think, aren't we? We're going to give you 3 minutes to strut your stuff and tell us in 3 minutes what you delivered as your talk for FameLab that won you the regional final.
All right.
Off you go.
Here we go.
Kate Feller.
There is a place on the earth where animals can make themselves disappear. It's called the pelagic environment. The pelagic environment is anywhere in the ocean where there is nothing but open water. There's nowhere to hide. It's just the same blue-green water in almost any direction. And just like in Star Trek, many pelagic animals have cloaking devices that help them avoid being seen in open spaces. One cloaking device is to cover your body in mirrors. Have you ever noticed how silvery some fishes are? These silver mirrors reflect all of the colors of the visible spectrum equally. And since this light is the same in almost every direction, these angled mirrors on their sides reflect light that's in front of them, and it looks exactly like the light behind them, totally hiding the fish underneath. Though these mirrors are great, obviously the best way to disappear is Harry Potter's invisibility cloak. But since most pelagic animals are muggles, they have to accomplish basically the same thing by having totally transparent bodies. The larvae, or babies, of many crustaceans, such as crabs, lobster, or mantis shrimp, have bodies that are so clear they look like they're made of glass. Even though you can't see their bodies, there's one thing that transparent animals can't make disappear, and that's their eyes. In order to work properly, all eyes, and we're talking all eyes, including humans, need to have dark, light-absorbing pigments. These dark pigments surround the individual light-sensing cells and isolate them from any stray light of their neighbors. If eyes didn't have these dark screening pigments, it'd be like drilling a bunch of holes into the body of a camera. The final image would be ruined. So, transparent animals have a problem where they want to be totally invisible so they don't get eaten, but they also need to be able to see. So they can't really have a transparent eye. But as my research revealed, some crustacean larvae have the solution. Covering the dark part of a mantis shrimp larval eye is a blue-green eye shine that looks just like blue-green glitter on a chocolate cupcake. Unlike the mirrors that we see in silvery fishes that reflect all of the wavelengths of the rainbow, this eye glitter only reflects the wavelengths of light that are behind them, which is blue-green, as we covered earlier. So, the reflection that this eye glitter gives off is matched to the background, which aids to disguise this opaque dark eye and overall lend the animal the ability to disappear. And with that, I'm going to disappear.
But do come back, Kate, because we enjoyed it very much. That's Cambridge University's Kate Feller and a very worthy winner of FameLab's regional final. Kate, thank you ever so much. You're listening to The Naked Scientists with me, Chris Smith, and with Georgia Mills.
Now, this year marks the centenary of splitting the atom. So this week, we're exploring the world of elements and nuclear physics. We'll be taking a look back to when the first atom was split, how we can use atoms to make energy, and how scientists are engineering atoms that have never existed on Earth before.
Well, that's a far cry from 100 years ago when our idea of what atoms were was very different. But it changed radically and rapidly, thanks to a Nobel Prize-winning scientist called Ernest Rutherford. His feats were so impressive that element number 104 in the periodic table, Rutherfordium, was named after him.
But just what did Rutherford do? To find out, Ricky Nathani went to the Cavendish Laboratory in Cambridge, where Rutherford first announced his landmark breakthrough.
Hi Malcolm, nice to see you. Pleasure. Yes, good. Yes. I am Malcolm Longare. I'm the Jacksonian Professor Emeritus of Natural Philosophy. I was head of the Cavendish Laboratory for 8 years, and I've written a history of the whole of the laboratory from its founding in 1874 until the present day.
And of course, today we're here to discuss the head of the Cavendish from 98 years ago now.
Yes. Rutherford came to Cambridge from Manchester in 1919 following the retirement of J.J. Thomson. Rutherford was clearly the outstanding nuclear physicist of the time. He had discovered the nucleus and had carried on doing brilliant experiments with very simple apparatus to establish the properties and nature of the nucleus.
In the early 20th century, scientists had established the existence of atoms, the tiny building blocks of the world. At the time, scientists thought that atoms were a blob of positive electric charge with negatively charged electrons stuck in it, like chocolate chips in a ball of cookie dough. The electrons, these negatively charged chocolate chips, were already known about, but nothing was known about the dough. Now, if you fire a bullet through cookie dough, you'd expect the bullet to go straight through, and that's essentially what Rutherford's team did. Instead of bullets, they fired tiny objects called alpha particles from a radioactive source into a sheet of gold foil. They could then measure these particles, these bullets, as they went into the foil and collided with gold atoms, a process called scattering. But something remarkable happened. Some of these alpha particles came flying straight back the way they came.
This is the famous statement by Rutherford. Says it was the most remarkable event of his life. It's as if you fired a large heavy shell at a piece of tissue paper and it came back and hit you.
So there must have been something very small and concentrated to repel these alpha particles. This wasn't behaving like cookie dough at all. So Rutherford's team investigated the scatterings and built up a new picture of the atom.
Rather than the positive charge in atoms being all distributed, say, in a sort of ball, there was an extremely tiny nucleus with the atoms, only about 100,000th of the size of the atom itself, which had all the positive charge.
So atoms are mostly empty. In our new picture, the electrons orbit around this tiny, positively charged nucleus. If an atom was the size of a football pitch, the nucleus, where all the positive charge and most of the mass is concentrated, would be the size of a garden pea in the middle of the pitch. The electrons would be whizzing around the stands with nothing between them and the nucleus. But what was actually inside this nucleus? To find out, Rutherford's team bombarded nitrogen atoms in the air with those same alpha particles to investigate further. And this time, they found something new being emitted.
Rutherford carried on doing these experiments, and by 1917, he had discovered that these particles really had to be very light, fast particles coming out of the nucleus, and made the suggestion that these were fast protons, and that was the nuclei of hydrogen atoms.
In other words, what Rutherford found was that there was a small, charged particle ejected from the nucleus of the nitrogen atom. This particle turned out to be a fundamental building block of all atoms, known as the proton. Now we have negative electrons and positive protons. But our atom isn't complete, because protons alone couldn't account for the mass of the nucleus. There had to be something more hiding in there. This mystery prompted another one of Rutherford's brilliant insights.
Now, in 1920, in his Bakerian lecture, Rutherford proposed, well, maybe there is a new particle, which he called the neutron, inside the nucleus, so that the nucleus consists of protons, hydrogen nuclei, and neutrons, rather than be lots and lots of protons neutralized by electrons. So that was the suggestion she made, and he and Chadwick carried out a very large number of experiments for the next 10 years, some of them extremely wild, trying to find evidence for this particle, and they didn't turn up. And it was only in 1930 two, that if they carried out Chadwick carried out the crucial experiments, a brilliant set of experiments in the matter of 3 weeks, which absolutely identified that there was a neutral particle with high energy coming out of the nucleus.
And so the picture of the atom fell into place. This nucleus in the middle of atoms was made up of positively charged protons and the aptly named neutral neutrons. Add the negatively charged electrons whizzing around the nucleus and voila, an atom. And by adding up different amounts of these building blocks of protons and neutrons to make up a nucleus, you could make up all the different elements of the periodic table that make up the world around us. So from the beginning of the 20th century, without a clue what atoms were, we arrived at the picture of the atoms we still use today. And it's no understatement to say that it was Ernest Rutherford who got us there.
He really is one of the greatest experimentalists of all time, if not the greatest. And the thing about Rutherford is that he would leave no stone unturned.
Which is surely the mark of a good scientist, isn't it? Malcolm Longer there, speaking with Ricky Nathvani at the Cambridge Cavendish Laboratory, where Rutherford made many of those seminal discoveries.
So now we have a clearer picture of the structure of atoms, but why does this matter? Well, it wasn't long before scientists realised that atoms lock away enormous amounts of energy, which is what holds these particles together.
This enormous power was demonstrated all too plainly during World War II with the creation of the atom bomb. Today, thankfully, physicists are more commonly using the energy of atoms in the nuclear energy sector. And that generates, in fact, 1/6 of the electricity we consume here in the UK, and in France it accounts for 3/4 of their electricity production. But what's the principle behind it? Well, Paddy Regan is from the University of Surrey and also from the National Physical Laboratory. He has the unenviable task of, in 5 minutes, explaining to us how does a nuclear fission reactor work? Paddy, how do we get energy from nuclear power?
The main thing to remember, I think it was mentioned in the previous section, is that the atomic nucleus is very, very, very small. Very, very small. And the reason it's very small is because the fundamental force that holds together the particles that make up that nucleus, we call it the strong nuclear force, acts over a very, very short range. And that range is something like 100 million millionth of a centimetre. What that means is that force is very, very strong, and that extra binding or strong force between, if you like, the sticking glue between the protons and neutrons in the nucleus adds a little bit of extra energy to the system. So listeners will be familiar with the only equation that sort of matters in physics, which is the famous Einstein one, E equals mc squared. And that idea is that energy and mass are sort of two interchangeable products, two sides of the same coin. And the idea is if you've got a very, very tightly bound, stuck together nuclear system, some of the mass is converted into what we call binding energy. Not very much, only about probably less than 1% of the total mass of the nuclear system is binding energy. But if we can release that, and that's what happens in nuclear fission, we can release an enormous amount of energy that's sort of held together and compact in there, a little bit like bursting a balloon by pricking it with a needle.
And in this instance, what's the nuclear prick that you use to burst that nuclear balloon then?
Well, it's the particle that was just mentioned earlier. It's the neutron, and a very interesting particle, the neutron. So it wasn't discovered, as the previous gentleman said, until 1932. That was almost 30 years after the discovery of the nucleus itself. And the reason it's hard to discover or hard to find it is because it has no charge. There's another interesting thing about the neutron in that if you have a neutron on its own, a sort of lone standalone neutron, it only survives as a neutron for about 10 minutes. It naturally radioactively decays. But when it's bound inside an atomic nucleus, it can basically live forever. So the little bullet, the little magic bullet that tickles the specific radio or the specific chemical element that we use in most nuclear reactors to cause nuclear fission, which is uranium, is processing a very, very slow bullet of this neutron material, and it's just captured by the uranium nucleus, and that tiny capture causes the nucleus to be unstable, to wobble a little bit and split up into two smaller fragments, releasing some of that binding energy. And the amount of binding energy that's released is about 1 million times more per energy release than you would have in a chemical reaction like coal burning, and that's why nuclear power is so efficient.
So we have a nuclear reactor, it has something fissionable, something capable of doing this in it, in this case uranium. Neutrons from that uranium hit the nuclei of other uranium atoms. They destabilise the nucleus, it falls apart, and in the process releases some of this energy and more neutrons, so it can then do this again.
And that's the trick. That's the idea of the chain reaction.
So why doesn't the power station melt down or explode?
There's a very precise amount of neutrons that are produced in each nuclear fission. And what you need for a chain reaction, a sustainable chain reaction, is exactly one of those nuclear neutrons is released to produce fission in the next generation. And in order to do that, you basically control the amount of neutrons that are in the reactor. And that's done by materials called control rods. So these are special elements, special lumps of material. They're made of things like boron or hafnium or cadmium, and they're material that basically drops into the reactor core and, for want of a better word, gobbles up neutrons, takes the neutrons away from causing fission on uranium, and the amount of control rod you put in will determine how many neutrons are still available to go on and cause fission. If you put in too much control rod, you basically don't have any nuclear fission that happens. They steal all the neutrons. If you take all of the control rods out, then you would have an increased amount of fission. Most reactors actually wouldn't be able to make a bomb just because of the nature of the uranium fuel that's in there.
Why does the uranium respond in this feedback loop by fissioning and breaking apart and producing neutrons, but the other chemicals you mentioned that are used to control the numbers of neutrons, they do not?
There is something very special about the element uranium, element 92 in the periodic table, and that is it's the heaviest element that occurs naturally on the planet. That means it's got the most number of protons in it for a naturally occurring element. And what causes fission is basically the repulsion between the protons in the atomic nucleus can be rearranged to give you a release of binding energy. So if you've got those 92 protons that form uranium, if you can split that uranium nucleus into two lighter elements where those 92 protons are divided into two separate types of chemicals or different chemical species, you get a big release in binding energy. And the biggest release in binding energy you'll get is from the heaviest occurring element, and that is uranium.
And where do we get all of the uranium that we use in our power stations from?
Well, uranium is ubiquitous over the Earth. About one atom in a million in the Earth's crust is uranium. It's all over the UK. It's in every bit of the ground here. There's plenty of deposits of it actually in the west coast of Ireland, around Galway, for example. But most of the mining is done in big countries like Australia, some bits of Russia, Kazakhstan, and South Africa, Canada. There are big geological deposits of concentrated types of minerals that are rich in uranium, and that's where most of the uranium comes from that would be used in nuclear power stations.
And how do we get energy out of this to turn it into electricity?
Well, it's a very simple idea. It's the same way that all power stations work, basically. It translates the energy that's released of these atomic nuclei as they're exploding, if you like, and it just turns that into heat. And it turns that into heat by interacting, by slowing them down in so-called fuel rods. It heats up metal, and that metal is then used to either heat up and boil water, or in the earlier type British reactors to heat up carbon dioxide and subsequently boil water. Boiling water turns to steam. Steam turns turbines, and you produce electricity in the way that any other power station would do.
Paddy, thank you for making it so simple for us. That's Paddy Regan from the University of Surrey.
You're listening to The Naked Scientist with me, Georgia Mills, and with Chris Smith. This week it's elementary because we've been looking into the heart of atoms.
Now, we've heard that we can split atoms apart to release energy, but the reverse of that process, which is pushing atoms together and fusing them, is an ancient process that's been, in fact, going on for billions of years. It's what keeps stars like our own sun burning. And this is also where the atoms that we're made of came from. Georgia has been hearing how.
From calcium, helium, lithium and titanium to argon, krypton, radon and xenon, our world is built from elements. You and I are mostly a mixture of carbon, oxygen and hydrogen, but where did they all come from? And what makes, say, an atom of silicon different from an atom of silver?
A chemical element is defined by the number of protons it contains in its nucleus. So every time you increase the number of protons by 1 unit, you are producing a new element.
So hydrogen has 1 proton, helium has 2, lithium has 3, and so on. This is Maria Luisa Aliotta. She's an experimental nuclear astrophysicist from Edinburgh University, and she's here to explain how to build the universe.
The first particles were created in the Big Bang. So originally there were essentially protons, neutrons, electrons, and there was a lot of gamma rays, high energy photons. Then eventually gravity starts kicking in, meaning that eventually all these particles and these kind of gas and dust starts contracting, and gradually you keep increasing the temperature of these gas clouds until eventually it is possible to reach temperatures that are so high that nuclear fusion can start. And this is when we say that a star is born.
Stars, like our sun, are mostly made up of this basic atom, hydrogen, which only has 1 proton. But stars can convert hydrogen into larger atoms through this process called nuclear fusion.
These protons, which are nuclei of hydrogen, they kind of scatter off each other because you have to imagine this gas has a certain temperature, and so all these particles are moving around, so they have thermal energy, as we call it. And so they collide with one another, and most of the times nothing really happens. This is like colliding billiard balls, okay? They scatter off each other and nothing much happens. But occasionally, some of these collisions may lead to the formation of a heavier particle, and in doing so, some energy is liberated. So this is the fusion process that occurs.
So thinking about this snooker table analogy, if you're playing snooker, the balls are obviously going to bounce off each other because of their tough outer shells. But if for some misguided reason you were to play snooker in the core of the sun, there is so much energy there that every now and then these turbocharged snooker balls would smash into each other and stick together. And this means you can make a heavier atom, like helium, from hydrogen.
And this is what powers our sun. And the sun has been converted hydrogen into helium for the last 5 billion years and will continue to do so for another 5 billion years.
This process also releases energy which we eventually see as starlight or sunlight. But what happens next?
After hydrogen has been converted into helium in the core of the star eventually has no longer a source of energy that can sustain the gravity of the outer layers, and so the star starts contracting. As it contracts, it heats up, and then eventually a new phase of nuclear burning can begin. And that's then the next stage, which is called helium burning, when now helium particles can fuse together to form, for example, carbon. And carbon can also interact with another helium nucleus and form oxygen. And so this is how heavier elements are then produced.
These heavier elements can only be fused in a much hotter star. As the more protons in an atom, the more energy you need to smash through that tough snooker ball exterior. And after a certain point, nuclear fusion just can't cut it anymore.
Iron is the last element that can be created through fusion of charged particles. Once iron has been created, it's no longer possible to obtain energy by fusing together two iron nuclei. And yet, elements heavier than iron, we know they exist. So the process that occurs then is a capture of neutrons on pre-existing heavy elements up to iron that then form heavier species. And this is how elements heavier than iron have been created, through processes of neutron captures.
So imagine our snooker ball atoms. The biggest ones can't stick with any more protons. They just bounce off their tough snooker ball shells. But they can stick to something else. Golf balls, aka neutrons. And if they stick to enough neutrons, they start to become unstable. And then one of these neutrons actually turns into a proton, therefore building a heavier element. This process can happen during a star's violent death throes, a supernova explosion. So all of these different elements get flung out across the universe and eventually find themselves in you and me.
When I was a child, there was a song by an Italian singer, Alan Sorrenti, and the literal translation of the title of the song was "We are all children of stars." I remember thinking, this is so silly. What do we have got to do with stars? But in fact, now I realize how very accurate that picture was. Yes, we are indeed stardust.
Professor Maria Luisa Aliotta there from Edinburgh University.
So that's how we get the naturally occurring elements or atoms that we have here on Earth. But scientists can also make artificial ones that wouldn't exist normally. And this is how last year we were in fact able to add a further 4 new elements known as super heavy elements to our periodic table. We're here to talk about these super heavy elements is Rodi Herzberg, and he's a professor of nuclear physics at the University of Liverpool. What are these things, Rodi? How did scientists actually make them in the first place?
What you do in order to get to these very heavy elements, the neutron capture mechanism that Maria Luisa just described no longer works up to that heavy mass. So you start out by 2 lighter nuclei and you start to fuse them together. So you throw them together as often as you can and you hope that eventually 2 of them will manage to fuse together and form one of these super heavy elements.
So you basically give them a huge amount of energy and hope that they collide hard enough that it will squeeze the 2 different nuclei together and you get the sum total of the 2 nuclei, the cores of both of those individual atoms adding together.
Indeed. Yet, this is a very delicate process because if you give it just a little bit too much energy, then they become so unstable that they will immediately split apart again. So it has to be very, very finely balanced.
And how many of these atoms, or how many atoms of these new elements have actually been made?
Let me take one of them, element 113, nihonium. Of that element, 3 atoms have been made by the Japanese group.
3?
Don't laugh. 3 atoms. Not only that, but it took them about 9 years to produce the 3rd one.
Goodness, and how do you actually detect when you've made a new atom of nihonium, for example?
It's a bit gruesome because you detect them by watching them die. The alpha decay that has been discussed previously is a very characteristic way for the nucleus to die, to decay to a different one. And if you measure those decays, then you can get a very characteristic sequence of alpha decays that you don't know. And finally, the same nucleus ends up in a couple of alpha decays that you do know. And those give you then an anchor point. Each alpha particle is 2 protons and 2 neutrons. So you can do the math and work back upwards to what you originally must have had.
Got it. So by watching really carefully, you're measuring these radioactive decays and you're seeing the particles coming off. So you know something is decaying. And if you add up all those things and you work out what you end up with, you can add them all back together to work out what you must have started with. And then you know you've discovered a new element potentially.
Indeed.
But if they're so unstable that they only hang around long enough to fall apart in a fraction of a second, and 3 atoms have been made in 9 years, why are we bothering to make these things?
Because just the fact that you can make them teaches us an awful lot about nuclei. And there are many, many places where you cannot do experiments, so you need to have a very good understanding of what the binding forces inside a nucleus, inside a very complicated system like a nucleus are. And the best way to test this is if you go to very extreme systems. Just because 3 atoms of this configuration of protons and neutrons actually were living long enough that we could detect them and do some physics with them, that means that our theoretical models have to be able to get that right, and that's a big challenge. And if they can do that right, then they can also understand how the elements are made in stars, how the nuclear waste that we may want to incinerate can proceed. All of that comes indirectly from these.
Could we also use them as stepping stones? Even though they may individually be short-lived, is it possible that you could leapfrog off of one of them if you quickly add something else to it and make an even bigger element? You make something where the nucleus is stable and it won't immediately fall apart, and then you've got some exciting new chemical you can do something really, really impressive with?
I think you can already do some impressive chemistry with some of them. For example, with fermium or with einsteinium, people had a little macroscopic vial of einsteinium in their hand that they could do experiments with. It's a question of quantity, and if you increase your capability to create more, better beams, better targets, then you can make more.
Rodi, thank you very much. That's Rodi Hertzberg, and thank you to our other guests this week, Maria Luisa Aliota, Malcolm Longear, and also Paddy Regan.
And now it's time for Question of the Week. Ricky Nathvani has been putting his best foot forward looking into this question from James.
Hello from Australia. As part of my exercise regime, I climb the stairs in our house. Is it more efficient to take 2 steps at once or take each individual step? And following on, is one tactic better for improving cardiovascular fitness, muscle strength, and so on?
Who needs a gym membership when you have stairs, right? But which method will require more energy and give you more of a workout? Step forward Dr. Dan Gordon, a physiologist and athlete himself from Anglia Ruskin University.
So if we take a standard flight of stairs, they have a typical height of about 18 centimetres and the depth is also about 18 centimetres. Additionally, we have an additional cost associated with the lengthening and shortening of the muscles. So if we're going to look at this, we're going to have to make 3 assumptions. The first one is that using every step would have a quicker step rate than taking 2 steps at a time. The second assumption is that taking 2 steps at a time would be associated with the greater height and length displacement per step than 1 step at a time. And the third assumption is that stepping rate does not change over time.
That makes sense. 2 at a time is slower, but it involves greater amounts of work to get up the extra height and length. So which one is more efficient? Throw some numbers at me, Dan.
We can estimate that for a standard flight of stairs, that 1 step at a time would be associated with an oxygen cost per step of 0.6 mils per kilogram per minute, compared to 1.1 mils per kilogram per minute per step when taking 2 at a time. So, taking 2 steps at a time would cost more energy and work your heart harder, despite lower muscle actions. The reason being, these actions have to be more forceful to overcome the increased height.
So 2 at a time wins for the workout, unless, like me, you want to be as lazy as possible, in which case stick to 1 by 1. But which method is better for James if he wants to build either muscle strength or cardiovascular fitness?
Well, this is a bit harder to answer. We've previously assumed that the stepping rate is constant. However, this would not be the case, as we know that body temperature starts to rise, energy stores would start to deplete over time. Given that there is an energy cost using 2 steps at a time, we can rightly assume that this would induce fatigue sooner compared to 1 step at a time. Also, given that when taking 2 at a time, you are stepping more slowly, but using a greater force, and knowing that using high force at low speed is better for building strength, we could apportion 2 steps at a time to being more strength orientated. To develop cardiovascular fitness, however, we need to maintain the exercise for a prolonged period of time without getting too tired, which seems to fit with the 1 step at a time approach.
There you go, James. 1 at a time is better for cardio, but 2 by 2 builds strength better. Thanks, Dan, for your help with that one. Next time, we'll be sending out this question from George.
When watching a film or documentary, a falling bomb or a missile always has a descending sound or a whistle. Why is this? Does it mean that if the missile fell down a bottomless hole, the sound would go subsonic?
If you think you know the answer, let us know. You can find us on Twitter or Facebook.
And that is it for this week. Thank you very much to Ricky Nathvani, who put the programme together for us. Next week, it's time for one of our Q&A shows. And if you'd like to join in, now's the time to send us any science questions to chris@thenakedscientist.com. The Naked Scientist comes to you from Cambridge University and is supported by the STFC, the EPSRC and Rolls-Royce. I'm Chris Smith, and thank you for listening. Bye-bye.